Hello, I'm Valentin, and today I will present our BlueSeer, an AI-driven environment detection via Bluetooth low energy scans. Environment detection refers to the ability for a device to recognize or classify its surroundings into broad categories. These categories could be home, office, street, transport, or shop. Environment detection is a very important ability for a device. For example, using environment detection, headphones can adapt their noise cancellation when we move or walk nearby traffic, for example near roads. A smartphone can turn silent mode on when we enter cinemas or theaters. Finally, a smartwatch can recognize between indoor running and outdoor running using environment detection. All of that without human intervention. But how can we automatically detect our environment? When we think of a smartphone contains a lot of different sensors it can use to detect its surroundings. For example, it could use its camera or microphone and use then computer vision or sound recognition to be able to detect between a shop and a house. We can also use the GPS. The GPS provides very accurate localization. Finally, we can use the Wi-Fi access point names or the cellular information or maybe accelerometers. But when it comes to IoT devices, for example, a fitness tracker or an IoT sensor deployed somewhere, these devices do not provide as many sensors available. For example, they might have some accelerometer or a temperature sensors and a wireless radio to be able to communicate. All these sensors are not equal when it comes to accurate environment detection. For example, a camera or microphones are very accurate, but a user doesn't want to take out his camera and start recording around them just to be able to detect the environment. At the same time, I do not want my microphone to turn on at any time just to be able to infer my environment. This raises privacy concerns. A GPS is very accurate, but it is the most energy-hungry sensor on device, and we cannot run them on small IoT devices. Accelerometers are great at recognizing movement and where we are moving, but it's quite bad at detecting in which environment we are currently. In this paper, we show that the Bluetooth low energy radio is the only component needed to be able to accurately detect and classify our environment. And we use the following idea. We have this following intuition. We think that each environment has a unique wireless fingerprint. For example, in a home environment, you will see a lot of static devices like your home assistant or smart lights, smart light bulbs. On the other hand, in the street, you will see a lot of devices moving around. You will walk nearby some pedestrians and you might receive packets from their smartphones. But as they move away, you will stop receiving these packets. In offices, you might see a lot of smart keyboards that you would not see otherwise in a home environment. So each of these environments has a unique wireless fingerprint that is unique enough so that we can distinguish between them. In this paper, we show that BLE advertisements, BLE packets, are the only input required to classify our environment. We present BlueSeer, an AI-driven environment solution specifically tailored to low-resource IoT devices. BlueSeer can classify between 7 environments, ranging from home, office, shopping, transport, nature, street, and restaurant. BlueSeer achieves 84% accuracy on low-power platforms and uses only 65 kilobytes of memory on device. Before diving into the design on BlueSeer and its evaluation, let's give a bit of background in Bluetooth low energy. BLE devices can advertise their presence using packets called advertisements. For example, headphones will advertise their presence so that phones or laptops can connect to them. Smartphones can also broadcast data locally, for example, for contact tracing. If we take an example of a smart speaker, the smart speakers will periodically send an advertisement to all nearby devices, broadcast information. And this advertisement will contain a lot of optional information. For example, the smart speaker can advertise its name as well as its services. For example, I can play music, I can control the volume, and so on and so forth. Then a scanner, for example, a smartphone, or in our case, an IoT device, can listen to all these advertisements and create a list of them. After scanning, a smartphone could connect to the smart speaker to start playing music. In our case, we just want to listen to all the devices around us. Great, now let's jump into the design of BlueSeer. This is BlueSeer architecture. Periodically, BlueSeer scans the wireless mediums for BLE advertisements, for BLE packets. After a scan, we extract from the raw data some informative features that we can then feed into an embedded neural network and classify our current environment. BlueSeer then gives the probability or the best environment to higher level application or higher level systems that can then adapt their behavior to the current environment. In BlueSeer, we scan for 5 seconds. After 5 seconds, we can have possibly a lot of different advertisements. For example, next to a shopping mall, we could receive hundreds of advertisements. But if we are in the countryside, we might receive 0 to 1 advertisements. Each of these advertisements has a variable length. For example, a smart speaker will advertise services such as playing music or controlling the volume, while home assistants will have way more services. Each scan returns a variable number of advertisements, and each advertisement has variable length. We cannot give this raw data straight away to a simple neural network. We need to pre-process that data. In BlueSeer, we extract 23 informative features. These features range from the total number of devices around us, also how many new devices did you hear from since the last time, or how many did we not hear from a long time. We also collect the received signal strength from all these advertisements, as well as the number of services advertised. All these features represent the density, the dynamicity, and the heterogeneity of our environment. And the idea is that all these components are unique enough to distinguish between a home and a street or a shopping mall. We then combine 5 scans to be able to model the evolution over time of our environment. Finally, we give these features from these 5 scans as the input to our embedded neural network. As a reminder, we target hardware that is resource limited. For example, the microcontroller might have a CPU limited to 100 MHz, and we might have less than 100 kilobytes of RAM available. Therefore, we go for a simple neural architecture with only one hidden layer made of 500 neurons. A model, after quantization, takes 65 kilobytes on device memory. And we need 12 milliseconds for inference. And this neural network is able to classify between 7 environments: restaurant, street, transport, home, office, shop, and nature. To be able to solve the task of environment classification, we need data. We collected over 70,000 samples in all of these 7 environments. One sample equals 25 seconds or 5 scans. We keep 62,000 samples for the training and 8,600 for the final testing and evaluation. What's very important is that we have different locations for each environment because we want to generalize well. For example, for the home environment, we collected data in 3 apartments and 2 houses. For the transport class, we collected data in buses, in cars, as well as in trains. Finally, our training and testing data are collected on different days. Sometimes they are even collected in different locations. For example, for the shop, we went for the training data in shop A on a Monday We then went on a Wednesday to a shop B to be sure that our data is different enough. For our home data, we collected training data on Monday and Tuesday, and then collected the testing data on a Friday. The problem is the following. Samples are very highly correlated next to each other, so we need to make sure that several days passes between training and testing, so that maybe the environment has changed, to test that our system is general enough. Right, let's go into the evaluation. We tested different neural architecture for BlueSeer and compared them to baselines taken from the classical machine learning approaches. Specifically, we tested decision trees and random forests. We see that decision trees and random forests barely achieve up to 80% accuracy when it comes to environment detection. On the other hand, BlueSeers using neural networks achieves always more than 80% and up to 84% accuracy. We also show that multiple hidden layers do not improve the accuracy. They only increase the memory usage. In the end, we select one hidden layer with 500 units because it offers the best accuracy, up to 84%, and only uses 65 kilobytes of memory out of the 100 we have available. Now let's look at the per environment performance of BlueSeer. We trained 10 different models and show that on average the accuracy is around 84%, where the best model was 85% accuracy. We see that BlueSeer is very good in static environments. For example, it reaches almost 98% in offices, and it reaches almost 99% in home and restaurants. On the other hand, it performs a bit less in dynamic environments. For example, let's take the shopping class. We see that BlueSeer only achieves 71% accuracy in shopping. And the problem is shopping is quite dynamic. There are a lot of people moving around you, and it's very similar, for example, to the street environment. Then BlueSeer only achieves 75% in nature. The problem is the following. For us, nature contains both city parks as well as the countryside. Problem is you will see a lot of other people working in city parks, while you might be alone in the countryside. Some of our classes might be too broad, and to be able to have the best performance, we might need more fine-grained environments, such as city parks and countrysides. This is the same for transport. Transport contains bus, train, and cars. This category is too general and would need to be separated to achieve an even better accuracy. Now we look at the importance of features used by BlueSeer. As a reminder, BlueSeer uses 23 features. Here we remove some of these features and see the overall impact on accuracy. What we see is that it's the combination of all 23 features that gives BlueSeer its strength. For example, the number of services has a very high impact on the accuracy, but also the receive signal strength has a very high impact on the performance. It's by combining all of these different features that we extract from our raw data that we can achieve up to 80+% accuracy. In conclusion, we show that BLE advertisements are the only input required to classify our environment. We present BlueSeer, an AI-driven environment solution tailored to low-resource IoT devices. BlueSeer can distinguish between 7 environments, ranging from home, office, shopping, transport, nature, street, and restaurant. BlueSeer achieves 84% accuracy on a low-power platform and uses only 65 kilobytes of memory. Finally, we make BlueSeer open source so that you can all try it. Thank you for listening to this presentation.